Okay, today is section 1-4, which is building functions from functions. So we can make new functions by building them from each other. So 1-4, building functions from functions. So first of all, we have different operations of functions. This is pretty much a review, but we can add, subtract, multiply, and divide functions. So if we have two functions that are f and g, then here's what we have. So our two functions are f of x and g of x. So if we're adding, then that would mean, well, that we're finding the sum, I guess. So the sum means that you would add f plus g of x. Sometimes it will look like this. F plus g of x is equal to f of x plus g of x. So you just take whatever they're both equal to and add them together. If we're finding the difference, then that would look very similar. It would be f minus g of x, and that would be equal to f of x minus g of x. And you would just replace the f of x and the g of x with whatever their function is. Then if we're finding the product, that would just look like this. We would multiply f and g together, so f and g of x, and that just means we're going to take whatever f of x is and multiply it by g of x. And then a quotient, so we can divide them as well, would be f divided by g of x, and that would just be f of x over g of x, and that is assuming that g of x does not equal 0, because if you had a 0 in your denominator, that would be undefined. So, for example, what if we have f of x equal to x squared and g of x equal to the square root of x plus 1, we can add, subtract, multiply, and divide all of those. So if I'm going to, we can also multiply it by itself. And it's only defined on the domain, on the intersection of their domains. So whatever the domain is for x squared, which if you graphed it, it's negative infinity to positive infinity. The domain of this would be where x plus 1 is greater than or equal to 0, because it can't be negative, so x is greater than or equal to negative 1, which would mean from negative 1 to infinity. That means whatever we're going to add them together, they're only defined on the domain of the intersection between these two things. So wherever they overlap, which would just be on the domain of the restricted one. So if I find what f plus g of x is, and it can sometimes be written with or without a parenthesis around both of them, but it usually will, that would be f of x plus g of x. So that would look like x squared plus the square root of x plus 1. Can't combine them because they're not like terms, so you just leave it like that. And if I think your book wants you to state the domain that it's on, it's only true for the domain of g of x, because that's where their domain intersects. So that would be addition. Subtraction would be f of x, or f minus g of x, and that would be equal to x squared minus the square root of x plus 1, with the domain just being the same. And the domain is going to be the same on all of them that we do. So then f times g of x would be x squared times the square root of x plus 1, which you can't combine those either, so you just leave it like that with the domain from negative 1 to infinity. And if we did division, f divided by g of x, that one is going to be x squared over the square root of x plus 1, and the domain is going to be look the same. You can just multiply, so I guess that's for this one. You can multiply the same, you can do any of these operations with any two functions. So I could even do like g, so g times g of x, which would just be whatever g is. In this case, it's x plus 1 times x plus 1, or it's times the square root of x plus 1, which would just end up being x plus 1, but it is still only defined for negative 1 to infinity. So hopefully that domain makes sense. It only works on the overlap of your domain, of the original function. So, there's another operation that we can do with functions that is not necessarily an operation, I guess, but it's called the composition of functions. And what the composition of functions is taking one function and putting it inside of another function. So you're creating a brand new function from that function. So how it looks is, and this may be a little bit of review, it looks like that, f of g, that's how you read it. So f of g of x is equal to f, and then you're plugging in that g of x equation in place of x in the f equation. So it's read as f of g. So you always want to work from the inside out. Composition can be done with discrete functions and continuous functions. So when we're let's see. Yeah. So with continuous functions, so for example, let's say we have f of x is equal to x squared, and in this case, let's make g of x x minus 3. So if we want to find f of g of x, then that's going to be equal to f of g of x. So we're going to take this g of x here and put whatever it is equal to, which in this case is x plus 3. We're going to plug it in place of x in our f equation. Sorry about that. So when we do it, it would be f of x minus 3. And x minus 3 is going to go in place of x in our f equation. So we had x squared as our f equation. So we would plug in that x minus 3 and have that be squared, and then evaluate that. So x minus 3 squared is really x minus 3 times x minus 3, so you could distribute your x, which would give you x squared minus 6x plus 9. So f of g of x is equal to x squared minus 6x plus 9. You can also evaluate this for a value. So let's say I wanted to find f of g of 3.5, and there's 3.5 there instead of x. That means just you'll plug in 3.5 for x in the f of g equation. So that would be 3.5 squared minus 6 times 3.5 plus 9. Or you could have done it in your g of x equation. So let me write this. So this would end up being 6 times 3.5 plus 9. So that ends up being 30. So you can do it this way. So that's option 1. Option 2 would be to find f of g of 3.5. So figure out what f g of 3.5 is, and 3.5 minus 3 would be 0.5. And then find f of 0.5, which in this case would, wait, that's not right. What? I didn't do this right. That's my bad. That really should give me 0.25. I forgot the 3.5 squared part. I'm an idiot, so sorry about that. But if I find f of 0.5, then I do 0.5 squared, which gives me 0.25. So it works to do it both ways. So composition works kind of works like that. You can do composition with any of our functions. So another example, just to have another example of composition. So let's use f of x as e to the x this time, and g of x as the square root of x. So if I'm finding f of g, so I'm going to find two things. I'm going to find f of g of x, and then I'm going to find g of f of x. So f of g means that I'm putting g of x in place of x in my f equation, so I'm finding f of the square root of x, which would end up being e to the square root of x. And if I'm talking about g of f of x, that would be g of f of x. So you're going to plug in the f of x in place of x in the g equation, which would be the square root of e to the x, which I know looks weird. That's okay. Okay, so finding the domain of a composition. If you're asked to find the domain of a composition, like I said earlier, the domain has to kind of overlap. So this is another example. So find the domain of a composition. So I'm going to start with f of x being equal to x squared minus 1, and g of x being equal to the square root of x. So if I list my domain out for both of those so I know where they overlap, this domain, the domain of a quadratic, is always negative infinity to positive infinity. This one would be anything greater than 0, so this domain would be from 0, including 0, to infinity. So just keep that in mind. So the domain of the first function and the domain restrictions of the second function, they should be put together essentially. So if I'm finding g of f of x, that would be g of f of x. I'm going to first find a composition. I'll talk about the domain in a second. So that would really be g of whatever f of x is, which is x squared minus 1. So then I'm going to plug in x squared minus 1 in place of x in my g equation. So that would be the square root of x squared minus 1. And we kind of combine the domain restrictions. So this is f of g, or g of f of x, but I need to include the domain restriction. So the domain of this function is where x squared minus 1 is greater than or equal to 0. And if you remember solving these, like from at the beginning of this unit, you got to find the zeros or factors of that. So that would be x plus 1 and x minus 1 is greater than or equal to 0, which on a number line you'd plot negative 1 and 1 are the zeros for both of those. They're closed circles, and then you got a test point. So if I tested 0, just because they're going to alternate, if I test 0 on my original equation up here, 0 squared is 0 minus 1 is negative 1 greater than or equal to 0, no. So that part isn't true, but the ends would be true if I tested those. So the domain of my composed function is negative infinity to negative 1, and then from 1 to infinity. So the domain for the composed function can be different than the domain of your original functions. So usually, and the reason I'm doing this is because in your book it will ask you to find f of g of f, or f of g and g of f, and then they'll ask you to state the domain of the composition. So you just find the domain of the composition excuse me, after you do that. So decomposition is kind of working backwards. So if I'm given, let's see, we'll call this decomposition. So decomposition would be something like this. So given a function, oh sorry, I almost sneezed again. Given h of x, find functions f and g such that h of x is equal to f of g of x. So saying that f of x, or h of x is representing the composition. So we're given h of x, and h of x would be x plus 1 squared minus 3 times x plus 1 plus 4. So we're kind of given it in a way that it's easy to pick out what was placed in place of x. So this and this are in place of where an x may have been. So x plus 1 is going to be our, what we put in for x, so g of x is equal to x plus 1, and f of x would be this with x's in this spot and this spot. So the f of x is going to be x squared minus 3x plus 4. So a lot of those you can kind of just see what the function is that was placed inside, and you can go from there. There's a couple possibilities for some of these, like they aren't going to be exactly the same. So if that's my first example, here's another example. So let's say h of x, in this case, is the square root of x cubed plus 1. So you could kind of make it up as you want to. So you could say that maybe g of x, if I'm saying this is f of g, g is what got placed inside. If I say g of x is x cubed, then f of x would be the square root of x plus 1. That is one possibility. Or you could say this, you could say g of x is equal to x cubed plus 1, and f of x was just equal to the square root of x. You can kind of come up with different scenarios that could potentially work. I think that is all I'm going to go through today. If you have questions from this assignment, then we can, well, yeah, we'll take a couple review days when I get back to go over questions that you have. Yeah, and go from there.